Good morning, students. Today we will try to understand fractional distillation. This particular procedure is similar to the distillation with slight difference. Now let's try to understand what that particular difference is. Now to separate a mixture of two or more miscible liquids for which the difference in boiling point is less than 25 Kelvin. So this is a technique that is used to separate two miscible liquids. It means these liquids are soluble in each other and the difference between the boiling point is less than 25 Kelvin. The apparatus is similar to that of simple distillation except that a fractionating column is fitted in between the distillation flask and the condenser. The difference between a distillation and fractional distillation is this fractionating column. The beads provide surface area for the vapors to cool and condense repeatedly. Here the fractionating column is filled with glass beads. Now what is the function of glass beads? As the vapors rise, they hit the glass beads and they condense back. Now let's try to understand this whole setup. This is a stand and this in turn is connected to the fractionating column, and here below the fractionating column we see the distillation flask. This is placed on a stand and there is a burner over here which supplies heat, and to the side we have the condenser, and finally we have a beaker or a conical flask that collects the liquid. Now first step, we start heating these two miscible liquids. Let's consider the miscible liquids to be A and B, and the boiling point, consider A to have 30 Kelvin as a boiling point whereas B to have 40 Kelvin. The difference between the boiling point is less than 25 Kelvin. That's why we see we need to go in for the fractional distillation technique. Now, since you are heating, both the vapors A and B both will rise up the fractionating column. Now the glass beads, as the vapors are rising through the fractionating column, the vapors hit the glass beads and then it falls back. But it is only A that will have enough kinetic energy to pass through all the barriers that the glass beads is providing and then rise up and finally get condensed. It will have enough kinetic energy at 30 Kelvin to pass through all these barriers and finally get condensed, whereas B will get condensed at 40 Kelvin. Now suppose this fractionating column is not there. See, the difference between the boiling point is so less that both the vapors can easily rise up together and then they can condense and we get a mixture of both the solvents, right? So what is happening? So the whole, if fractionating column is not there, we are not going to get two pure solvents. We are going to get a mixture of solvents. Okay, that's why we are using this fractionating column. At its boiling point, we see it gets maximum kinetic energy. B is also trying to pass up the glass beads, but it does not have the kinetic energy to move through these glass beads because it has not reached 40 Kelvin temperature. 40 Kelvin temperature, that is its boiling point where it has maximum kinetic energy. But whereas A has already got the maximum kinetic energy. In normal case, if we don't have this fractionating column, then there are chances that the vapors will get mixed up and finally it will get condensed and we will not get two pure solvents. That's why we are using this glass beads. Next, we will try to understand separation of components of air. Now air is a mixture of gases and we need to separate out these gases. So how do we do it? First, we need to filter the air. The air might have certain dust particles which has to be filtered. Now the air is made to pass through a chamber, the first chamber, where it is compressed under pressure, or the molecules are brought close to each other under pressure. Then the next step, what we are doing is, in the second chamber, we are supplying cold freezing water so that we reduce the temperature. Here we are increasing the pressure, here we are decreasing the temperature. So what happens over here in the next chamber? In the third chamber, we see that because of the increase in pressure and decrease in temperature, the first component to be separated is carbon dioxide. Now carbon dioxide separates out as dry ice. It is nothing but solid form of carbon dioxide. So here, because of increase in pressure and decrease in temperature, it has got converted into solid. So in the third chamber, we see carbon dioxide separates out as dry ice. Now slowly, by means of expansion jet, we are increasing the temperature so that it gets converted to liquid. And that liquid we are passing through the fractionating column. In that fractionating column, nitrogen and argon comes out. We separate nitrogen and argon. Then finally, in the last chamber, liquid oxygen separates out. I'll repeat once again. Here impurities are filtered. We are increasing the pressure, decreasing the temperature in the second chamber. Here in the separator, the solid carbon dioxide separates out because we have increased the pressure and decreased the temperature. Then by means of an expansion jet, we are slowly converting that solid air molecules into liquid, and then it is passed through fractionating column where nitrogen and argon is separated. Finally, in the last chamber, liquid oxygen is separated. And this particular flow chart is mentioned in your textbook. You can go through it. Whatever I have explained, it is put forth in form of a flow chart. And they have also given the boiling point of oxygen, argon and nitrogen. And second one is percentage air by volume. How much of the various components are present in air. Next, moving on to crystallization. It is a process that separates a pure solid in the form of its crystal from a solution. Here we are obtaining pure solid in form of crystals. Crystallization technique is better than simple evaporation technique. We will learn why. Some solids decompose, or some, like sugar, may get charred during heating through dryness. Now what happens is, when you are heating solid, water molecules present in them evaporate, and if you heat further, it might get burnt or it might get charred. Some impurities may remain dissolved in the solution even after filtration. On evaporation, these contaminate the solid. Sometimes even after the filtration procedure, some impurities may remain. So that's why in crystallization you don't have these drawbacks. Then what are the applications of crystallization? Purification of salt from seawater and separation of crystals of alum from impure crystals. Now we will try to understand how crystals of alum are obtained from impure crystals. First step, take 100 ml of water in a beaker. Heat it till it starts boiling. Okay, you have to heat it till the water starts boiling. Then to that, add a small amount of impure alum powder to the water and stir it with a glass rod so that it gets evenly distributed. You need to add the impure alum and stir it with a glass rod. Then add more alum powder and continue doing so till alum stops dissolving in water, obtaining a saturated solution of alum. Now what is a saturated solution of alum? It means the space between the water molecule has been completely occupied by alum molecule. No, you cannot dissolve alum in the water. It will not take it. That is saturated solution. So you need to make a saturated solution of alum. Once you have obtained the saturated solution, then filter the solution using the filtrate. Then the filtrate what you have obtained, in that filtrate suspend a small crystal of pure alum tied with a thread into the solution. You're taking a pure alum and you're tying through the thread and you're suspending it in that solution. Now what will happen? Allow it to cool for 24 hours. Crystallization will take place. Now the alum molecules that are present in the filtrate will get attracted to the pure alum and the crystals start building up or forming. So thereby we get pure crystals of alum and the impurities are left behind in the beaker. This is with respect to the crystallization technique and a very important one.